states electrons are emitted from a metal surface when it is illuminated with a suitable electromagnetic radiation. Name the effect described. So electrons are emitted. This part is like electric, and electromagnetic radiations, this part is the photons, because we have the photons related to electromagnetic radiation. So you have got it right. That's photoelectric effect. The second part of the question says the variation with frequency f of the maximum kinetic energy ek of the emitted electron is shown in the figure. So when light falls, electrons are emitted with different kinetic energy, which is plotted against the frequency of the incident light. So if we plot these points, we get a straight line graph. So as it is a straight line, so we compare it with the standard equation y equal to mx plus c, and a similar equation in this case we have that kinetic energy ek equals to hf plus negative of phi, where phi is the work function and h is the Planck constant. So the first part of question B says use the figure to determine the threshold frequency. So threshold frequency is the frequency, the minimum frequency required to knock out an electron. At that instant, the kinetic energy of the emitted electron is 0. So we can use the graph to find out at what point the kinetic energy of the emitted electron is 0 and what's the corresponding frequency to that 0 kinetic energy. So if we plot it for 0, we get it here 6.4. Each small box is 0.4, so that is 6.4. But not to forget to write this 10 raised to 14 hertz in your answer. So the answer is 6.4 into 10 raised to 14 hertz. The next part of the question says use the figure to determine a value for the Planck constant. The question says use the figure. So if we look at the figure and the equation, so we know that the slope of this graph is the h, the Planck constant. So the slope of this graph is h equals to the change in the kinetic energy over the change in frequency. So we can pick any 2 points on the graph and can work out the change. So we pick these 2 points, point 1 and point 2, and we write their corresponding values on the x and y axis. So these are the corresponding values for these 2 points. So the change in ek, the kinetic energy, is actually the change in the y-axis, and the change in the frequency is actually the change in the x-axis values, which are these. Using these values in the above formula of the h, we get the value of the h as 6.3 into 10 to the power minus 34. Okay, that's right, 10 to the power minus 34. And its units are joules second. The part C of the question says on figure 7.1 draw a line to show the variation with frequency f of the maximum kinetic energy ek of the emitted electrons for a second metal which has a lower work function than in B. So the work function phi is given as hf naught. If work function is less, it means the threshold frequency f naught will be less, but the slope will be the same. So we need a graph line having the same slope but starting from anywhere at a lower frequency than the 6.4. So like this red line. Is it clear? So moving forward, the last part of the question states the kinetic energy of the electron is described as maximum. Suggest why emitted electrons are likely to have a range of values of the kinetic energies for any one frequency of the electromagnetic radiation. Actually, we use the word maximum for this equation. Ek equals to hf minus phi. So if we are using the minimum amount of the like energy required to knock out, so these electrons are knocked out from the surface. So the electrons which are knocked out from the surface, they have greater kinetic energies. Maximum kinetic energy is for those electrons which are knocked out from the surface, but electrons which are knocked out from deep inside will have less speed. Deep inside the surface, which are emitted from deep inside the surface, has lower energies.